Right, this time we're going to do the same but with an Abaqus file, so Inp file. So while I was preparing for these talks, I wrote an importer for such files using Python. So you can find it here on GitHub. So just make sure you got NumPy, which is usually the case, and you got this script that can import a file and export them into STL file. One parameter that is important is this one, because my experience is that some of the files got the normal vector in one particular order or direction, and some other file in the other direction. And as we rely on the direction of the normal vector to do the simulation, to compute the L buffer, it's important that we have normal vectors that are outward. So if they're inward, we're going to reorder the vertices to make sure that the normal vectors are outward. So first we need to retrieve Inp file, and there is one that you can download from this address. So we do that. It's downloading, and we make sure we change it to a more precise name. So now we got this Inp file. Now I would like to have this file installed, so I'm going to download this file. So if I click, and just download this file. Right, so it should be there now, and you can see this is here. Make sure this is executable on a Unix system, and now I can run this program. So with the input, which is my Inp file, and the output, which will be just the same but in STL. And it's going to export it. So now I should have a new file, which is here, and we're going to import it with where is it? Right, I don't have file with MeshLab, just to check that this is okay. So we go back to the same directory, this one, and try that one. Open. And you can see here the normal vector are inward, which is why it's all black. So not very good. Right, I'm going to try again, but flipping the normals this time. So let's import the file again. And you can see this time this is beautiful. This is all fine. Can we look at the triangle so you can see the surface? And if we do, no, I don't want to see the surface. So if I do that, you can see that we have tetrahedrons, not just triangles. So we really have a volumetric mesh in that case. So we're going to see if we can simulate an X-ray projection from that object. So we can shut that, I guess. Can even close it. I forgot some details. So because this is an ASCII file, it's going to be rather large. So if we go in the terminal and look at the file size, it's about 27 megabytes. So what I tend to do to reduce the size of the file, I export it as a binary STL file. So here I make sure that there is a tick in that box. And if we compare the two now, you can see that now this is a lot smaller, so less than 6 megabytes. So that's pretty much why I'm doing it. Right, so as we saw earlier, the normals are inverted, so we have to keep that in mind. So let's start the Python interpreter. And what I'm going to do is to load packages to start with, so matplotlib, etc., etc. The package for the X-ray simulation and the package to import the Inp files. We could set up the environment to simulate X-ray images to start with. So first we need to create an OpenGL context with a window. Set up the X-ray beam, so we can start with the position of the beam of the source. And we'll use a parallel source in this example. ATKF again, and set the detector position. So a position, an orientation, how many pixels, the space between the two consecutive pixels. Now we're ready. We can load the data with the Inp package that I provide. And here we have vertex data. So numbers are x, y, z. So for each vertex there are 3 coordinates, and this is a big array of coordinates, of points. That many points. Depending on the Inp files, there might be more than one mesh in the file, so we need to check the length of the index for the vertices. So here there is only one, so there's only one model in the file, and there are that many triangles. Oops. And well, we could print so that's the length. What I wanted to do is not that, I want to print the first triangle. So here this is the first mesh, there's only one, and the first triangle of that mesh, and here this is the index in the vertex set. The first point of the triangle, second point, third point. We could write the STL file if we wanted to. I realize that some of the vertices in that array are not used in the mesh, and that could be a problem to compute the bounding box. So we have to make sure that the vertices that we use are the ones from this array. So we need to compute the bounding box by hand, and we're only going to look at the vertices used by triangles. So what we're going to do is a big for loop that's going to look at the triangles that we need and the vertices that we need for these triangles. So we go through all the triangles, and for each triangle we go through all the vertices, and we need to make sure that if we don't have a value for mean corner, where we just copy the vertex. As well, you have to check against the values that you already got, so you need to keep them in. Same with the max. And here, well, I did not define the known type, so I'm going to define the known type. And I forgot that maybe I have to import the, so I'm going to do it again. So I'll copy paste from my text editor. Problem with indentation. Okay, so I have to do it by hand, I guess. Right, we could look at the values. And this is the min and max corners, right? We can compute the range. And that's going to be used to center the mesh. So we're going to go through all the vertices of the mesh and just translate them so the mesh is centered. So a big for loop through all the vertices of the mesh, minus min, plus minus, so minus the min, minus half the range. Now our mesh is centered. We're going to load the mesh into the graphics card. Yeah, let's import the NumPy package. Right, so we imported the mesh known as male model, the vertices, and the triangle index. And here I have to make sure that I flatten the array, because we're using one-dimensional arrays. So I use NumPy to do that. This time I decided that the model will be made of hydrogen. So this is the element hydrogen. And I'm going to add it to the simulation. And now we're ready to compute the X-ray image. We can save the image. And now I'm going to look at what it looks like using ImageJ. So ImageJ is loading. I saved it as text file. So import text image as mailmodel.txt. And here is our simulated data. If we wanted to, we could use matplotlib to plot the data. What is wrong here? Oh yeah, I have to. Well, we could try with different color scales. So a log scale can be nice, and a power law as well. So these are the three lookup tables that I use. Right, so the log scale and the power law, and what I'm missing is without lookup table, so just a linear lookup table like what you use normally. So what we'll do next is to simulate a tomography acquisition. So we're just going to go and compute a few X-ray images all around the objects that we're scanning, and then we can reconstruct it. That will be in the next video.